All righty, friends. Look at this. We're back again. Not gonna lie, this is my fourth one today. Phew! We are doing math and loving it, loving it, loving it. All right. Let's see here. We want to go right to that one right there. And there it is, friends. We've added more derivatives to our fun and excitement. All righty. And I went ahead and told you guys, if you want to see all the derivatives we're doing this year, you'll find them on page 378. Yep. Now, good news is we're already halfway through all the derivatives for the entire year. So we're doing pretty well. But again, I'd still probably, if I were you guys, I'd make up some flashcards and just start doing flashcards just 5 minutes a night. That's it. That's it. So far, we've been looking at all kinds of derivatives. And let's go and write out there what these are here. We've been doing we've been doing first derivatives. Today, we're going to look at higher derivatives. So we're going to get past this idea of first order derivatives. And we're going to get to some higher order derivatives. And I'm going to show you, oh, that was a horrible line. I don't like that line. Oh, I like that one much better. All righty. So let's just talk briefly about some higher order derivatives, okay? And using things we talked about. So we said, what if we had a position function? And we said the first derivative, or the derivative, another name for a derivative is first derivative. And we said this was velocity. So if we start with position, we can take a derivative to turn position into velocity. Well, it turns out velocity can go down even further. It says that, in other words, the first derivative of velocity is acceleration. Okay. The rate at which rates increase or decrease. So if velocity is the rate of change of position, then acceleration is the rate that the rate of change is changing. So in other words, we'd actually say that acceleration is the second derivative. In other words, it's two derivatives away. So think of it this way. I have position. And I take the derivative of position to get velocity. Well, if I take the derivative of velocity, I get something called acceleration. By the way, if I take the derivative of acceleration, I get something called jerk. So, but we're not going to get into that one. I need to erase it. Prime. Maybe. That's a very hard prime to get. There we go. So start with position. P prime of t, or the first derivative of position, is velocity. V prime of t, or the first derivative of velocity, is acceleration. There we go. Now I got it right. So notice there's two levels away to get from position. So two levels away to get from position to acceleration. Well, what if we wanted to go right to acceleration? There's two levels away. So what we'd say is that P double prime of t, or the second derivative of P, would be A of t. This leads us to this idea that we can have more than one derivative. We can have different layers of derivatives. It's a great way to say it. So, for instance, we have f of x. That's a function. Well, f prime of x, that would be the first derivative. f double prime of x would be the second derivative and we can just keep bringing this thing all the way back down there if we wanted to. The f triple prime of x, and you guys probably are kind of seeing where this is going, that would be the third derivative and f quadruple prime of x. You can't, is it getting a little redundant now? It should be. All right. That would be the fourth derivative. And friends, we could go through all the way to infinity, infinite number of derivatives. Now, we wouldn't want to do that. Wouldn't want to do that, but we can just keep doing derivatives over and over again because all these functions have different layers. So before we come back and we take a look at this position, velocity, acceleration stuff, we're going to spend a little time dealing with that today. We're going to go and take a look at some functions. So here's what I want you to do. I want to know f double prime of x when f of x equals x cubed minus 5x squared plus 7x minus 1. I also want to know f triple prime of x when f of x equals the square root of x plus 1. All right, friends, pause the video, take a little look-see at this, see what you come up with. All right, here we go. So my first derivative. By now, we're hopefully starting to get a little bit better at some of these derivatives here. I'm not going to show every step along the way now. I drop the exponent, subtract 1. I have a negative 5 down here, so when I drop the 2, negative 5 times 2 makes that negative 10, and subtract 1. The exponent of 1, drop the exponent, subtract 1, constant is 0. So here's my first derivative. And now I'm going to get my second derivative. Six x minus 10. All right, let's try the other one. We are going to do, first thing, you guys all hopefully by now know that I don't do radicals. Everything is always going to be an exponent. All right, first derivative. And we're just going to keep it right on going. Second derivative. So I end up with negative 1/4 x plus 1 to the negative 3/2. Oh, friends, we're cruising now. Get ready. Here comes the third derivative. There we are. And again, I say this all the time, friends, math is so much more fun if you add a little sound effect to it, and I tell you what. Just taking different layers of derivatives, it's not the most enjoyable thing, but if you pretend like you're driving a race car while doing it, oh, you got something going. All right, so got a couple derivatives here, got ourselves some equations. I think maybe we should try some more of these here. I'm not gonna lie, I like this eraser tool. How fun would that be in real life? You know what? You get a ticket, eraser tool, right? I mean, these are the kind of things I think about. You know what? You're up to bat, strike out, no harm, no foul, eraser tool. Try it again. The reality is half of y'all do it when you go bowling anyways. Oh, eraser tool. That I didn't get a gutter ball. I got a spare. You can never give yourself a strike though. I mean, everybody saw. All right. Why don't you guys try some higher order derivatives if we make them trig? Oh, so the second derivative when f of x equals secant x, or how about the fourth derivative for sine of x? All right, friends, go ahead and pause the video there, and let's see what you guys come up with. All right, here we go. Secant, remember that one. That's one of my special derivatives here. So I get secant x tangent x. And uh-oh, careful, because now to get my second derivative, I'm going to have to do a product rule. I got a first function, we'd call that f of x, if I wasn't already using f of x. And the second function, we can call that g of x. So I got a product rule now to come up with my next one. It's not optimal, but not anything we can't handle. All righty. Here we go. Let's go plug some stuff in here. So the first thing I got, my first function, secant x. And then my second function, my derivative of my second function. So that would be secant squared x. And then I have my second function, tangent x. And then my first function, or the derivative of my first function would be secant x tangent x. Not plus, that should be just times. Oopsies. All righty. And again, we could simplify this if we wanted to. No reason to. If it was multiple choice, on a multiple choice test, yeah, you'd clean it up a little bit, but you know what? Tomatoes, tomatoes. All righty. Let's see if we can play a little bit more here. What about this other one? What would that be? Now let's try it. First derivative. So the derivative of sine would be cosine. I'm pretty good at that one. Second derivative of cosine would be negative sine. Third derivative, well, we're getting up there now. So the negative is going to stay there, but the derivative of sine is cosine. So let me just rewrite that one there. Whew. So I'm now at a negative cosine. And now the fourth derivative. There we go. We got cosine would be a negative sine. So negative times negative again makes that a positive. Take a look at this. The fourth derivative of sine actually is sine. So there's this little pattern. First derivative, so go sine, cosine, negative sine, negative cosine, and back to sine. It's this little pattern, a pattern of 4, and it eventually repeats itself. I believe that kind of reminds me of of imaginary numbers a little bit. We'd say that's periodic. Again, don't need to say that, but we could. So there we go. So higher order derivatives just means keep doing them repeatedly. But now what we really wanted to spend our time with here is not necessarily doing a higher order derivatives per se, but more dealing with position. So we said position the first derivative of position is velocity. The second derivative of position is the first derivative of velocity, which is acceleration. Every time we can kind of build a little bit on particle motion, we're going to. So let me give you guys a little scenario here. A particle moving along the x-axis has a position modeled by a function. From 0 to 11. Time t from 0 to 11. Determine the following. Velocity of the particle when t equals 2. Acceleration of the particle t equals 2. Speed of the particle when t equals 2. Speed is not velocity, they are related. We'll talk about it in a second. And determine if the particle is speeding up or slowing down when t equals 2. Yeah, so this is going to be what we're dealing with here. How in the world are we going to do this? Probably should give you an equation too, by the way. That might be helpful. So let's see here. We're going to go x of t. So I'm not using p of t this time. I'm using x of t. X of t equals, what did I write down? That's today. There it is. T cubed minus 2t minus 11. Yeah. All right. So that was weird. What happened here? Better. Okay. So let's try this here now. Velocity. Well, if we know that x of t, so we have our velocity equation. There's our position. Now notice I didn't give you guys, oh man, oh my goodness. Give me 1 second here because I just realized I did not write that right. There we are. That was supposed to be T squared. Couldn't read my own handwriting. You're going, Williams, I can't read your handwriting on the screen. Probably true. You try writing with a mouse. See how you do. All righty. Cap. So T cubed minus T squared minus 11T. So I want T cubed minus T squared minus 11T. And yeah, we're good. All right, friends. So I want you to find the velocity. Okay, go ahead and pause the video and do it. All right, so you guys know now that velocity is the derivative of position. So we got 3T squared minus 2T minus 11. So if I plug 2 in for my velocity, I end up with 3 times 2 squared minus 2 times 2 minus 11, which would be a whopping, friends, and I kid you not, how about negative 3? I got a negative velocity. In other words, my particle is moving backwards along the x-axis. In other words, it's moving towards the left. What about the acceleration? Friends, why don't you guys go ahead and find the acceleration? Go for it. All right, so if I take the derivative of velocity, I get acceleration. And again, this is the second derivative of position. So that means I get 6t minus 2. So plug it in. Plug in our 2. And I would have 6 times 2 minus 2, which would be 10. All right. So speed is essentially the absolute value of velocity. It's velocity without direction. So if I ever want to know what speed is, if I ever want to know what speed is the absolute velocity, absolute value of velocity. So speed is velocity without direction. Doesn't matter if it's negative, doesn't matter if it's positive. Speed is the absolute value of velocity. So if I'm looking at my little problem here, I know what my velocity is. It's negative 3. So speed at t equals 2. That's going to be the absolute velocity, absolute value of the velocity at 2, which is the absolute value of negative 3, which is a positive 3. So speed doesn't care if it's positive or negative. Speed is the absolute value of velocity. All right, and one other thing here, the last thing is speeding up or slowing down. Now this one's a little bit different. We've got to know a little bit about physics. Each of these velocity and acceleration, they're forces. So if velocity, we're using red for velocity. If velocity is negative and acceleration is negative, the forces will be going in the same direction. Therefore, they're going to be helping each other out. If velocity is going in a positive direction, that's not velocity. And acceleration is also positive. They're going in the same direction as well. When the forces are going in the same direction, when the vectors are going in the same direction, they would allow the particle to speed up. But notice if the velocity is negative, but the acceleration is positive, the forces are acting upon each other, and you end up getting things that are working against each other. And if they're working against each other, the two forces will cause friction, and they cause each other to slow down. So here, when they're both negative or they're both positive, they're speeding up. They're going faster. If they're fighting against each other, notice, it's like running into the wind. Even though you feel like you're running at the same rate, you're not. You're getting slowed down because you're running into the wind. If velocity and acceleration have the same sign, it's speeding up. If velocity and acceleration have opposing signs, it is slowing down. So let's see if we can't write that here. Speeding up. If it's speeding up, that means velocity and acceleration have the same signs. If it's slowing down, if they have opposite signs. Have opposite signs. Probably should have just typed this out on Zoom, but we're using the mouse. It's all right. Have opposite signs. All right, so let's take a look at this. Part D, is the graph speeding up or is the graph slowing down? So this is where we're going to go through here now. We're going to look at what our velocity was. The velocity was a negative value. The acceleration was a positive value. Therefore, we would say that it is slowing down. It's not always slowing down, so we got to make sure we say when it's slowing down. Slowing down at t equals 2. You leave off the t equals 2, I got to die here. So make sure you add that. Because don't put v of t, put v of 2. Be specific. Because v of 2 is less than 0. And a of 2 is greater than 0. Okay? So higher order derivatives we use a lot when we're dealing with particle motion. So friends, I think it's time for you guys to try one of these here. The one I'm going to give you guys, let's see here. This one's going to go from 0 to 8. And I want you to test it when it's at 1. And is that what I want? I think so. Got to move this out of the way real quick so I can get here. I'll move it back. Right there like that. And I can go ahead and type in our equation. X of t equals t cubed minus 5t squared minus 13t. All right, friends, go ahead and pause the video and see if you guys can take a little gander at trying to solve some of these. All righty, here we go. Let's see here. Velocity. Velocity is the derivative of position. So if I take the derivative here of position, I should be able to get my velocity. So we have 3t squared minus 10t. And here's our position right here that I'm basing off of, minus 13. So when I plug 1 in here, figure out my velocity, I get 3 times 1 squared minus 10 times 1 minus 13. And friends, I believe that's going to be a negative 20. All right, here we go. The derivative of velocity would give me acceleration. So we're going to use our velocity equation right here. So I get 6t minus 10. And we're going to figure out what our acceleration is. And friends, that would be negative 4. So that was part B. We already did part A here. And we're going to be adding to particle motion a lot throughout the year. So this isn't like a one and done. But we want to make sure we have a decent understanding before we go too far. All right, so speed at t equals 1 is the velocity, the absolute value of the velocity of 1. So that's the absolute value of negative 20. So the speed is 20. And then after that, for my speeding up or slowing down, I go back, I look at my velocity, it's -20. My acceleration is -4. Now notice, even though they're both negative, that's okay. It just means I'm speeding up. Speeding up at t equals 4 because v of t is less than 0, and a of t is less than 0. That should be 1. Speeding up, not 8, 1. There we go. Got to be specific. So again, got to make sure that I know that I'm not speeding up the entire time. I'm only dealing with speeding up when t is 1. And I'm not, my velocity and acceleration are not always negative, but they are negative at when t is 1 as well. So just be very specific. Don't leave those open-ended. All right, friends. Well, that takes care of that. So, hey, another one down, right? We're cruising. So good luck and I'll see you guys in the morning.